Even people that are both pro-nuke and anti-nuke are interested in the subject. And we have wondered largely about things like the time to build, as nuclear plants have been terribly long in lead time, and which drives their cost up. We're also interested in the cost effectiveness of small nuclear reactors, the safety of them. They're proposed to be a lot safer. The economies of scale by building the smaller units. And Sham has had extensive experience in the nuclear power generation area, and he's worked with several of the more promising developers of SMRs. He's well qualified to elaborate on the questions we all have with regarding to SMRs, and so I'm really happy to introduce him, and there'll be some time for questions afterwards, or maybe you'd prefer to take them as we go. I don't know, Sham.
Either way is okay. Generally, I mean, I do training classes, so I'm somewhat familiar with the process. Sometimes it is best to answer the question right away. Uh,
Okay.
we we have an hour about, right?
Yes, we do. Yeah, well, you can
Okay.
spill over a little bit if
A little
necessary.
bit. Okay. I wanted to ask you that. And so, yeah, sure, absolutely. And then at the end, of course, I do have a Q&A session
Hmm.
or a slide. So either way works. And please feel free to have a conversation.
Okay, Sham. Well, why don't you take it away?
All right. All right, folks. So very quickly, thank you, Bob. You've already given background. I'm originally from New Delhi, India. I've been in this country 47 plus years, graduate school in North Carolina, consulting engineer, worked at a nuclear power plant, BWR, boiling water reactor in Iowa in 1985. 1 year rotation in quality assurance, never to leave QA. Joined PG Trojan in 1992, which was an 1100 megawatt PWR pressurized water reactor, and I was manager of supplier quality. After we decommissioned it starting in 1993, supported Trojan in a dry fuel storage configuration and reduced hours with PG and provided training and consulting all over the globe, 35 plus countries and all 50 states in the US, I'm proud to say. And somewhere along the line, I got a chance to work with Steve West starting, I think, in 2005. And that trauma has not left me yet. So, we will cover what is an SMR and why. Basics of nuclear power, fusion versus fission, traditional nuclear power plants, what failed at TMI, Three Mile Island, Chernobyl, and Fukushima, um, SMRs around the globe, special features of an SMR, the ultimate, excuse me, it's jumping for some reason. Ultimate safety features of the SMRs. That's the main selling point of SMRs. And of course, cost. NewScale and TerraPower, those are the two companies which are here in the Northwest, Pacific Northwest, that I've worked with extensively. In fact, my last audit at TerraPower was 2 months ago. So let's go and get started. So what is an SMR? So first of all, SMR, small modular reactor, and is a small reactors are defined as those reactors that are generally 300 megawatts or less, and they offer various benefits: safety, small physical footprint, reduced capital investments, although none of them have been installed yet. So the initial cost is high. Ability to be sited in locations not possible for larger nuclear power plants, and provisions for incremental power additions. They are modular, so they can come in 2 packs, 6 packs, 12 packs, etc. So benefit there is that you can fuel one of or two or three of those units or packages while the rest are still performing. In a regular nuclear power plant, when a single large reactor shuts down for problem of refueling, there is no power coming. But in SMR, because of its modular format, it will be available. So why hunger for electricity? The global electricity demand is projected to grow very rapidly, 50% higher than the previous decade. Worldwide capacity of nuclear power is expected to grow by 2030, ranging from 437 gigawatts to 748. So as you can almost doubling it up. 20, go ahead, please.
No, go ahead. I didn't mean to interject.
20 countries without previous experience in nuclear power are exploring the possibility of constructing nuclear reactors. And more as some justification, as I just said, modular versus a single large reactor shuts down for problem or refueling. So let's get the basics of any nuclear power plant. Reactors typically use uranium ceramic pellets that are stacked together into a sealed metal tubes called fuel rods. These pellets are the size of the end of your small finger, really. And there is a little picture here of the size of the pellets. I've seen them being made in various parts of the world. Sorry about this. I don't know what's going on here. A reactor core is typically made out of 200 plus fuel assemblies. So it starts with the pellets in a fuel rod. Multiple fuel rods are bundled together in a fuel assembly, and then the fuel assembly goes into the reactor vessel. In the reactor core, typically it would be a light water reactor versus a heavy water reactor. Both coolant and the light water is the coolant and the moderator. The moderator helps slow down the neutrons produced by fission to sustain the chain reaction. Control rods can then be inserted into the reactor to reduce the reaction rate or withdraw to increase it. The heat created by fission, and mind you, we are talking about fission right now, turns the water into steam, which spins the turbine to produce electricity. That's the basic concept of any nuclear power plant. So there is always, or not say, but there is common conversation about fusion. Just for fun, I added the word confusion versus fission. So fusion is when the atomic particles, tritium and deuterium, are put together. They hit into each other. They create helium and neutrons, and the energy then comes out. This is a very tough process. We as a humans, we've been trying this for nearly 60 years, and now it seems like we are pretty close to reality of fusion. Fission, on the other hand, is a neutron that hits a nuclide. It produces more neutrons, and then, of course, it also produces energy. And once these neutrons go out, they hit other particles, and typically uranium 235, 238, and produce more neutrons and more energy until they are controlled and managed by the control rods. Control rods are basically called neutron poisons. They are generally made out of boron chemical, and they absorb neutrons. They're called neutron poison, like I said. All right, a traditional nuclear power plant, a PWR, which was at Trojan, was 1,100 megawatts, and the system is very simply defined, where inside the containment. Are you guys able to see my cursor?
Yeah. Yeah.
So inside the containment, there is a reactor, there is a pressurizer, and there is a steam generator. Of course, at Trojan, we had four steam generators and one pressurizer, or pressure tank as it's called. That's kind of a safety device. So the steam generator produces the steam, which runs the turbine, which runs the electric generator, and then of course the steam comes back to the steam generator. At no stage in a PWR there is a direct connection between the radioactive water which is inside the core, because it is supposed to be isolated through the steam generator, because from steam generator the water at high temperature and pressure comes back to the reactor. Unfortunately, at Trojan, we were having some issues with the steam generator tubes that were starting to leak. So for a good while, we controlled them by plugging them, literally, so that the capacity of the plant went down. But that was one of the main reasons why we had to shut down Trojan. Although, quite frankly, the better option would have been to replace the steam generators. But unfortunately, we had some less than courageous decision makers, and that didn't happen. So that is the basic concept of a pressurized water reactor. Any questions? Okay, moving on to the other well-known, well-established in the US type of reactor, which is called a BWR, a boiling water reactor. In this case, the steam and hot water is actually steam, runs from steam into the turbine directly, and then from turbine, which turbine again, turbine does the electric generator work, or provides, rotates the steam, the electric generator, and the steam then comes back to a condenser and goes back to the reactor. In this case, both the turbine and the condenser are contaminated with radioactive materials, because they come out of the core, and therefore there are some other protections and other things that we have had to use over the years. But it is a well-established type of system. Yes, one could say, hey, what happened at Fukushima? Because they were all BWRs. And unfortunately, well, this is, again, I'm sorry, BWR. They were all BWRs in Fukushima, but the reasons they were different, and I'm going to talk about that in just about a minute. So the question that comes in, what failed at the various famous or infamous events in the nuclear industry? The first one was TMI. The second one was the famous Chernobyl, and then, of course, Fukushima. So the TMI, which is a Pennsylvania 3 Mile Island plant, partial meltdown was caused by a stuck open pilot valve. Also, human error happened. Operators misread control room instruments and mistook a loss of coolant accident. But the root cause, and I had the fortune of working with a gentleman who in 1979, subsequent to 1979, was one of the teams that investigated TMI, and he was very generous in sharing the root cause analysis that he submitted to the President Carter at the time. And he shared with me that in their team's mind, the root cause of TMI was, in addition to human error, too much confidence was placed in the regulatory compliance as a substitute for real safety. Chernobyl in 1986 in Ukraine was caused by a combination of a flawed Russian reactor design, specifically the control rods and operator errors during a safety test at low power. I've had the opportunity to go to Ukraine many, many times, way before all these bad things in the war, etc., happened, because Ukraine, since their independence in 1989, in the early 2000s, has been wanting to transition over to Western technology. So I was actually training and teaching them quality systems, the US quality systems called 10 CFR 50 Appendix B. And during that period, I got to meet a bunch of people who used to work at Chernobyl and were now working at other 14 different nuclear power plants in the country of Ukraine, where they used to have 15. And I've had the opportunity to work with them and learn a bunch of things what happened at Chernobyl. Fukushima, Daiichi, yes, was in Japan 2011. The disaster was caused by a magnitude 9.0 earthquake, subsequent 15-meter tsunami, which incapacitated backup generators in cooling system. That was basically was a bad design in the sense that the cooling generators were, backup generators were located at a place. The assumption was that the magnitude of the earthquake that can happen around Fukushima would not be more than 7, at the most 8. They were never designed for magnitude 9. And of course, most of us are engineers, so we understand that the difference between 8 and 9 earthquake is significant. All right. So now let's move on to small modular reactors. First of all, folks, let's be clear. Yes, sir.
Could I ask a question, please?
Absolutely.
On the root cause analysis, the comment about regulatory compliance versus actual safety, is that they were just following the rules, but the rules weren't necessarily addressing safety in particular, or were they behind were they not in alignment with what should be done? Could you explain that just a little bit?
Sure. So just to give you a quick background on it, the basic, or I should say fundamental, which is actually a gold standard of quality management system, or QA, for nuclear power plants came out in 1970. It was called 10 CFR 50 Appendix B. All nuclear power plants, even if they were in the course of being built, are and were licensed to that particular program. It was only 8 or 9 years into that Appendix B when this event happened. Frankly, a lot of folks felt that the Appendix B and the guidelines that ANSI and 45.2 developed would be adequate for events, because there is a design basis accidents that were presumed in the quality management system. So most companies, most utilities at the time would meet the standards and felt comfortable that meeting those would suffice. At this stage, what I was told by the team that did this investigation, that they should have, not only should they follow the rules, of course, regulations, but they should look for any other symptoms, any other things that may not have been envisioned in the regulation. So that was kind of the conclusion. Did that help you a little bit?
Yeah, and so just to follow up to that, then,
Yeah.
going forward and looking at current practices, is there a separate body, or is it in the operational design that someone is looking at those other factors in terms of safety? They're taking outside of whatever the document might say.
Yes. Actually, would you believe that literally within the last month, NRC, Nuclear Regulatory Commission, has come up with 10 CFR 53, which actually gives that flexibility. They actually let the engineers and the designers define safety and what are called credible failure modes. So
Okay.
yes, we are starting to look at it more than regimented safety requirements, but also design-based, probabilistic risk assessment-based safety measures. That's a good.
And then we could assume then that that same thought process is being adopted then as we look at SMRs.
Yes, sir. And you will
Okay.
see those coming up. It's an excellent segue for me, actually.
Thank you.
Well done. Thank you. So First and foremost, there are 100 plus SMR designs in the world. There is a great desire for the countries. 32 of them are gas cooled, heat pipe cooled, metal cooled, molten salt cooled, and water cooled. So I'm going to talk about at least two of them in a little bit. There is also a movement towards what are called micro modular reactors, MMRs. One of them is Kronos, which is the University of Illinois Urbana. They are gas-cooled reactors. The unit is helium-cooled and designed to produce up to 15 megawatts. So it's really a micro reactor, and the reactor stores heat in molten salt tanks for steam generation. Just an interesting fact in the front end, I will be talking to you about TerraPower, which is, of course, supported by Bill Gates and somewhere which is one of the more successful in this country, also uses molten salt tanks for steam generators. Then the coolants are water, heavy liquid metals, molten salts, and gases. And so those are the types of small modular reactors being built. This is a bit of a fun fact for everyone. You folks might know that we, as in US, in 1962, we had transported a 1.8 megawatt reactor installed in Antarctica. And that particular one, one second here, was called McMurdo, that produced electricity for light, heat, and desalination. The enrichment in that particular microreactor was 93%, which is typically the case in naval reactors also, versus all the other reactors that we are looking here, both SMRs and regular reactors. The enrichment is less than 5%. Unfortunately, this particular reactor on Antarctica was fraught with operational and radiological issues, and it was shut down permanently in just 10 years. Subsequently, it was decommissioned and shipped back to the mainland USA at a very high cost. Some 700,000 tons of dirt and contaminated materials, etc., were shipped back to good old USA for burial. So it was, I thought you might find this interesting. All right, so special features of SMRs. First thing and foremost is that they are flexi deployment, which means is that they are multi-modular power plants, like I said, 4, 6, or 12 packs. Factory fabrication and truck transport. Even a single module power plant, you can have a single module power plant if the needs are smaller. Connectivity, both you can do off-grid, and you can also have a microgrid. And of course, it can be connected to regular grid. It can be, the location can be on land or even marine. Applications, typical, these are just typical. Power generation for community, desalination, industrial, process heat, and of course, we are all hearing about data centers, AI centers, crypto mining, and that sort of thing. So district heating, hydrogen production, and remote, even military installation. So you can see these are some of the features of the SMRs. But then the most important thing is, and I did mention to you about the events we had, the TMI, Chernobyl, and to Fukushima. So the industry for developing SMRs had to address the basic features that were not available or are not available to the traditional nuclear power plant. So number one is, on the left-hand side, you can see, is natural coolant convection circulation, passive decay, and heat removal. No reliance on external power for safety function. This is where Fukushima got into trouble, because they were they were reliant on the emergency steam generators. One of the biggest things is no operator actions or AC power is needed for shutting down in case of an accident in an SMR. These are some basic features that we are expecting and demanding from SMRs. Controls are gravity driven and they are inherently stable. Cooling is natural and always on. So those are, and then of course, they are generally, almost all of the SMR designs are low primary and secondary pressure. Because as you can imagine, as engineers, you know that pressure and temperature and humidity are the main causes where in case of an accident, things would go really, really bad for a nuclear power plant. So with that said, let's talk the cost of SMRs. I'm sure that is something that this is brought up every time. So here is the story on that. In 2026 dollars, a conventional nuclear power plant is about $15 million per megawatt. 2 units at Plant Vogtle in Georgia, they came online in 2023 and 2024, came at $13 to $16 million per megawatt. They were originally claimed to, the claim to fame was it'll be between $7 to $10 million per megawatt. Turned out to be much more, I'm sure you've heard the stories of how the costs went crazy on those plants. Not a single SMR is operational currently. So let's be clear about it. So the cost estimates differ wildly. I've been working, like I said, with SMR, at least 2 companies very closely, and they just in the last 10 years, I've heard various different cost estimates. One of the recent one was in 2026 dollars, an SMR is estimated to be at $20 million per megawatt. So one might say, whoa, what are we talking about? SMRs are not less expensive. Well, the reason is that this is the first of kind we call folk cost. Because I just said that not a single SMR is operational as yet time. But the cost will likely go down substantially when they are the nth of kind or NOx, from folks to NOx. That's the terminology we use that in the SMR world. The last assumption I heard was that by middle of 2030s, so 2035 or so, SMRs will be between $4 and $5 million per megawatt. Future SMRs will be factory-based, mass production. And 1 second here, guys. I'm so sorry. I don't know what's going on with this. There will be factory-based, mass production, and oh boy.
How does that cost compare with wind, solar, or gas-fired turbines?
When you compare with the solar and I'm being told that solar and wind is about half the cost of SMRs. The issue is the wind and solar, the efficacy is about 29%, and the SMR will be over 97%. So the solution that is being proposed, and I was in China relatively recently, where they are building some huge batteries, BYD batteries that even PGE has bought. Those will help with what are called base loads that SMRs are able to provide. And of course, that the battery themselves, actually batteries and SMRs are kind of competing with each other in some ways, because batteries will have to be able to sustain a large amount of power so that they can support based on the charging that would happen from say, solar or wind. So let's see here. I'm sorry. Okay, so the future SMRs will be factory-based, mass production, have standardized design, and regulatory harmonization is already in progress. This is the one I was just talking about it a few minutes ago. A gentleman asked me a question about the issue at TMI. 10 CFR 53 has just been issued a few weeks ago, literally, and it is technology inclusive, it is risk informed, it is performance based framework for licensing modern reactors. And so what I mentioned about safety, what I mentioned about new kind of regulatory harmonization, that is going to help considerably with that. By mid-2030s, SMRs will probably be between $5 to $6 million per megawatt. That is the assumption. Any questions, comments? Okay. Moving on to, I personally have worked with both NuScale and also with TerraPower. So NuScale started in Oregon State University, Corvallis, as a research project in 2002. Is now a mission to bring small modular reactor to, oh my gosh, this is really, I'm so sorry, guys. I don't know what's going on with this. My apologies. To bring small modular reactor to global energy market. In September 2025, which is less than a year ago, a historic partnership was formed between Tennessee Valley Authority, TVA, and Entra Energy, launching the largest small modular reactor deployment with NuScale. So there is considerable excitement in the SMR world with TVA and NuScale. TerraPower, which is a Bill Gates backed TerraPower, Bellevue, Washington. Like I said, I just worked with them. Last received an environmental clearance for its planned natrium reactor in Wyoming from the US, from the NRC in October of 2025. And they've actually broken ground. They're building a training center, and I'm hoping to provide training there in the next year or two. The natrium reactor differs from most other reactor design in its use of a sodium-based cooling system, which, according to the company, allows the reactor to operate at lower pressure than water-based reactors, reducing the risk of meltdown. So it's very exciting from that perspective, sodium-based cooling. And I'll be showing you a sort of a diagram of how TerraPower system works. All right. NuScale Power is a like I said, a small modular reactor that uses a self-contained integral pressurized water reactor. It is a pressure water reactor similar to what I showed earlier. Designed, and each module is 77 megawatts per module. It operates via passive neutral, natural circulating, eliminating the need for a coolant pump. Reactor type is integral pressurized water reactor. Similar it's about 1/20th the size of Trojan core. Nucleus is the first and the only. Sorry, guys. I'm going to get there from here. Oh boy. Okay. Is the first and only modular reactor to receive a design approval by the U.S. Regulatory Commission. So they do have their design has been approved by the U.S. NRC. The module dimension is only 76 feet by 15 feet cylindrical containment. I've seen their 1/3 the size of their in Corvallis. They had a 1/3 the size of this representative reactor that I've personally audited a few times. The module weight is 700 tons in total and are shipped from the factory in 3 segments via truck, rail, or barge. This is what that NuScale reactor looks like. There is the containment on the outside. There is a pressurizer, very similar to the Trojan plant, much smaller, of course, 1/20th the size. Steam generators are there, reactor pressure vessel is there, and the reactor core is at the bottom. So it is 1/20th the size of a large reactor. Each module feeds one turbine generator train, eliminating single shaft risk. See, if you have single shaft risk, then the whole plant shuts down, which is true with larger plants that we have, the conventional plants. 100% turbine bypass capability, small, simple commercial grade components support the short, straightforward refueling outages. So that is NuScale for you. A little more on NuScale. Modules can be added incrementally. So if you buy a 2-pack, you can buy 4 more to get a 6-pack and so on and so forth. With the first module generating electricity while additional modules are being installed. Fuel is a standard light water reactor, fuel in 17 by 17 configuration, which is about 6 feet tall. I've seen some of these being built and they are very interesting. Refueling cycle is 21 months. A typical large nuclear power plants, they used to be annual. Now they have gone to 18 months. This is 21 months at this time. This SMR plant design is capable of withstanding severe weather, aircraft impact. They have been designed for that, electromagnetic pulse and cyber attacks. And the plant is operational objective is 60 years for NuScale.
What size of the TerraPower generators are you mentioned that?
I'm sorry, I didn't quite hear that. Bob, go ahead.
What size of the TerraPower unit?
It's coming up. Next slide.
Pardon?
I said next slide is coming up.
Oh, okay. Okay, sorry.
So in October 2020, the Department of Energy selected Natrium Sodium Fast Reactor designed for advanced reactor demonstration in Kemmer, Wyoming. That's where groundbreaking has only taken place. It used to be a coal nuclear power plant in Kemmer, and it is now decommissioned, the coal plant, and right next to it in the same campus, TerraPower plant is being built. The reactor operates at near atmospheric pressure, which is a big deal because that makes it safer. Circulating sodium through its core by pumps. Heat is transferred from the hot primary sodium pool to the intermediate sodium piping loop by means of 2 intermediate heat exchangers, which are located inside the reactor vessel, which is a big deal because then it's contained and can be factory manufactured and shipped. As of April 2 of this month, by leveraging NVIDIA and Omniverse, TerraPower has demonstrated that site-specific SMR engineering work that traditionally takes 18 months can now be completed in as little as 8 weeks. So I got to visit and interview and talk to a lot of TerraPower engineers, and they are very excited about this project that's coming down the pike. The Natrium safety evaluation it's a pool type metal fuel SFR with molten salt energy is the island. Simplified response to abnormal events, reliable shutdown, transition to coolant natural circulation, no safety related operator actions or AC power. That's a big deal. Technology based on US and SFR experience and inherent safety characteristics. Controls are motor driven. Run back. 1 second here, guys. Come on. Inherently stable with increased power or temperature. The cooling is in vessel, primary sodium heat transport, intermediate air cooling, natural draft, and reactor cooling with a draft flow. And the containment is low primary and secondary pressures, sodium affinity for radionuclides, and multiple radionuclides retention boundaries. So inherently, natrium is a safety oriented design. The interesting thing is that TerraPower is not stopping at natrium. They are actually going forward with a traveling wave reactor. But before we go there, let me show you how the natrium works. So the way it works is that this is the reactor itself. It has sodium, and molten sodium is the one that produces that causes molten salt to melt right in the reactor. Molten salt travels to a energy storage, and it is retained there as an immediate source of heat for steam generators. And then once the steam generator is producing energy, it would run the steam turbine, which would run the generator. But the beauty of this is that it is not dependent on the reactor continuously working, because the molten salt is the energy storage that is the source of energy for the steam generator. So that makes it more reliable. And in case of reactor had to stop for any reason, at least we have a substantial amount of energy. It's almost like saying something is battery backed. So it would continue to produce power, and hopefully by that time the reactor will be coming back online. But so natrium has that additional feature. Future with TerraPower, natrium and TRW. Natrium reactor is the near-term 345 megawatt sodium cooled fast reactor. It's beyond the quote-unquote SMR, which is supposed to be 300 megawatts, but for all intents and purposes, natrium reactor is considered an SMR. Integrated a molten salt energy system, allowing reactor to boost out, and it can boost energy too, besides storing, to 500 megawatts for over 5.5 hours, pairing well with the renewable energy, with renewable energy. Advanced development with construction plan for Wyoming, targeting by 2030. So that's the current plan for a natrium reactor at TerraPower. The next reactor, the future reactor at TerraPower, is called traveling wave reactor. That has a long-term focus, uses a small amount of enriched uranium to initiate a reaction, then breeds its own fuel. This is the magic part, the amazing part. It breeds its own fuel from surrounding depleted uranium-235. TRW can run on non-enriched depleted uranium for 40 years. Think about 21 months to 40 years or more without needing to be refueled. The goal is to drastically reduce nuclear waste and eliminate the need for fuel reprocessing and lowering operating cost. So that is the traveling wave reactor. And I saw some of the design work. Of course, it is in design right now. No prototype has been built. The prototype for natrium has been built, but not for TRW.
Who is taking the power from the Wyoming facility?
I'm sorry, who's taking the what?
Who's buying the power, is contracted to buy the output from TerraPower Wyoming facility?
Well, of course, I think your question is who will be buying, because it'll be 5 years before the plant is built. It will be the local county and the city of Khmer. They have already committed to buying that. And then, of course, there are also the state of Wyoming, which is kind of an interesting situation, being a state that normally would support coal power and all. They have already signed contracts to buy TerraPower's natrium reactor output.
Hmm. Interesting.
So,
Sham, I've got a question before
yes,
you
sir.
move.
Yeah,
So thinking about both these small modular reactors or this type of nuclear power,
yeah.
the question I have is I understand the differences in operation in terms of pressure and those kinds of things and safety, but one of the things that I wonder about is handling of the depleted uranium, and then what are the risks, safety risks, and also costs associated with handling spent fuel. I mean, is that a problem, or is it really not a problem at all, and it's just um, side noise?
Um, I'm going to be respectful for those folks, and not you necessarily, but I'm just saying who are concerned about the processing and handling
Yeah,
and storage of spent fuel.
yeah.
Absolutely. Earlier in this conversation, I was talking to Mike and Bob and a few of the other folks who joined earlier. This is genuinely a real cause of concern for us as a society. My personal belief is, and as you know, I've been associated with nuclear since the early 80s, that is something that we, and I say we mean the United States, have not handled it very well. We have had political and unnecessary other types of interruptions as well as uh, involvement that have not permitted um, a good solution for it. So, number one, we use fair amount of nuclear power in our naval reactors. You know, we use them for our ships and submarines. The fuel from that is reprocessable and is reprocessed. In as much as I admired President Carter, he was a nuclear engineer himself. He, based on some feedback or other things that he may have received, he made the decision that the civilian side of nuclear fuel is not going to be reprocessed because it would be traveling on nations' highways and this and the other. That decision still is affecting us, adversely affecting us. And then on top of it, we, as a nation, had put in $5 billion and a lot of effort and time and energy into Yucca Mountain for storage. That itself, both Republican and Democrat senators of that state of Nevada, went NIMBY, not in my backyard crap, and did not allow for Yucca Mountain to proceed. So therefore, our current traditional nuclear power plants, almost all of them, are housing the nuclear fuel that they have used. We don't have a real immediate solution. For example, there's one in New Mexico, there's one in Texas. They're talking about in 2026, they're still talking about interim solutions, interim storage. So,
Sham,
yes, yeah, please.
China is building now close to 25 nuclear plants under construction, and they have over 70 on the drawing boards. What are they doing with their nuclear waste, you know?
So, two things that I've heard is one, of course, that we are banking on some political courage and having a solution sooner than 20 years later. The other part is the SMR, in terms of quantity, they generate much less nuclear waste or nuclear. They like I just mentioned to you, some of them they use the same enrichment or in the nuclear fuel, but they produce in a total quantity much less. So it will be controllable, but they will have to have capacity to store spent fuel on site. They are called ISFCs, intermediate storage. I'm forgetting exactly. Trojan is an ISFC. So with these designs, they're also building storage capacity as we are proceeding and hoping that we will have a solution sooner than later.
So my feeling, Sham, was that because I went to school with a young engineer that was working on storage. He lived in the Tri-Cities, and this is going back into the 70s. So my assumption has been that it's not a technological problem as much as a political problem. Am I wrong about that, or is the technology just not advanced?
Europe does fuel processing. They also have dry storage and very deep storage tunnels or
Yeah.
deep underground this thing. But the quantities are significantly less.
Yeah.
Your point of being a political problem is more correct than
Okay.
a technological problem. We can process fuel, and it will bring down from let's say a bucket full to 3% of that bucket. Think about
Okay.
this.
Yeah.
We could reduce the waste down to 3%, and it'll be manageable.
Yeah.
So
That was my assumption. So that I think that's one of the challenges that not just for nuclear power, but really for this organization is to educate people so that the political process can advance to fall in line with the technology, the technological solutions.
very, very, very well said. And, of course, you folks in the sustainable group understand the climate effect, and you understand how we are having to deal with um, um, the climate impact and global warming, etc., better than anyone. And on the other hand, our need for energy is increasing, electrical energy, and so absolutely, I've sometimes I feel a little disappointed and actually dejected until I see some of these, which you're looking at it, some of those um, technological capabilities we have, and my hope is that we will work together and get some political courage and proceed in a more sustainable manner. So, folks, this was a kind of a quick rundown. I shared with you what is an SMR, why consider them, basics of nuclear power, fusion versus fission, traditional nuclear plants, what failed at TMI, Chernobyl, and Fukushima, SMRs around the globe, special features of SMRs, ultimate safety features of SMR, touched a little bit about the cost, and then talked about NuScale and TerraPower, present and future. So in terms of presentation, that's all I have. I'm, of course, open for conversation. I'm not going to call myself a designer or an expert in SMRs. I have worked with companies that have developed, as you've seen, and my interest and support is for this technology. So with that, open to any questions.
Hi, this is Kelly.
Yeah, hey, Kelly, how are
Long
you?
time.
Yeah.
Back to Bob's question, I think, we know Pacific Power or Pacific Core is surrounded most of Wyoming, and my contacts there have not mentioned anything like that, but I'll find out. Another statement on the supply of material and everything. Have you heard or seen of any shortage of supplies of material that would be used for this organization, this project?
Quite frankly, that is a major concern. With all the emphasis on steel and availability thereof, you are a supply chain expert, so you know better than I. Availability of steel and other things, the cost of commodities have gone up by 30, 40, 60% in the last couple of years, especially in the last 2 or 3 months with the war in Middle East. So I was talking to somebody at TerraPower recently, and they expressed great concern about it because these SMRs are much smaller than the full-size reactors, but they still need a lot of engineered products. And so, yes, that is a concern, and commodity pricing are definitely are affecting some of their thinking. The only good news, and it's kind of a ironic way to say it, because SMRs are 2 or 3 or 4 years down the road, we may have better situation on the steel and commodity markets by then.
Thank you.
Hey, Sham, I've got another question. GE and Hitachi have a consortium that's working to build SMRs, and they're proposing to build some up, and I believe it's the Montreal area. They were going to build several of them. Have you heard anything about that? What the status of that is, and whether their project is going forward or where they are?
Yes. So Ontario Hydro and GE Hitachi, they are together. They have signed a MOU with Ontario Hydro. So yes, and they're thinking about doing it at one of the existing plants because the environmental and other studies have already been done there, and the Canadians are very keen to have them. So yes, I hear that they are, just like some of the other ones I mentioned, TVA and others, they are proceeding with it. GE Hitachi design is also very looking very feasible. I've read that. I worked with Hitachi folks a little bit, and they are very keen to proceed.
Mm-hmm. Okay.
Notice a hand up there. Yes, sir. Go ahead.
Yeah, in terms of siting, I thought for a time now that with especially when you look at Snake River dams removal, those kinds of things, and also just the fact that along the Columbia River, we with climate change and potentially the impact of snowpack, has there been discussions that you know of in terms of retrofitting existing power plants or sites where there are dams with small modular nukes? And then just subsequent to that, I know that's probably not realistic in Oregon today, but even retrofitting Trojan, are those discussions taking place? Do you know of?
My understanding is that PGE, at least some folks at PGE, have cautiously approached NuScale for Trojan, for reciting a Trojan. Where that conversations are, I'm not aware. I've been gone one full year now. But there was definite, and I'm aware of that. In fact, the individual who met up with
It just
NuScale.
Yeah, it just seems like you already have transmission infrastructure there, and maybe other infrastructure. It's just why wouldn't we leverage those things?
I mean, I will supplement your point. It's not just the transmission; it is the environmental basis. The site is Trojan site is located on a solid rock where it is not subject, although we are all subjected to the big one, relatively speaking, that is a very safe spot to be. It's a basalt rock which goes, I don't know, 200, 300, 400 feet into the ground. So all of those commonsensical things that you're saying make sense. Unfortunately, it's what we just talked about. It is the political courage that we don't seem to have. And I'm sometimes hard on that bit more probably than should be, but man, it's just amazing to me how people just don't think it through.
Yeah.
These things are so feasible and so real.
Yeah, I appreciate you confirming my thinking, and I agree with you that the political problem is a greater task in front of us.
Yes. And then again, I mean, right now we are being told by Washington that the climate problem doesn't exist. We need to go back to coal. So, I mean, we've got some crazy crap going on there too. So it's a combination. Any other comments, questions, discussion? I mean, like I said, I'm able to share whatever little bit I know about this area because I'm truly interested in it and getting an opportunity to work with some of these local companies.
I would also say, just as another site, there would be the Boardman site. I think at one time back in the Whoops days, it was somewhat licensed or projected to have 4 nuclear plants, but that fell through, of course. But anyway, that's another site.
No, your point is good, Kelly. And then of course, Trojan was going to have a second reactor on site. It's called, Pebble Beach, it was going to be called. In fact, it was located in terms of where the whole system was going to be. So that was withdrawn. And of course, up near Olympia, there were 2 nuclear power plants. Even in fact, there are 2 cooling towers that are still up there. I'm forgetting the name of that area, but those plants were never built.
Is it SASIP?
So I think that sounds reasonable. Yeah.
I'm guessing.
Yeah, I think that does sound like right. I've driven by it, those, and as you know, we brought down the Trojan cooling tower in 2006, and that was quite a media event, although it didn't have any nuclear contamination. In a PWR, the cooling towers are completely disassociated with the reactor.
And SATSUP has a pretty close connection or location to the 500 kV grid.
Yeah, and it was supposed to be a very doable and feasible and reasonable design, and we as a society had a sort of a adverse reaction. I think it was after TMI that we, after spending all that money, there was many other nuclear power plants that were not fully built. Marble Hill in Indiana was one of those, and some of the reactors that I work with, they bought their equipment that was basically sold at 10 cents a dollar, all the valves, all the motors, all the good stuff, all safety related.
Hmm. Is that all the questions we have for today? Anybody else? So Sham, I want to thank you very much for your presentation. You did an excellent job, and I really enjoyed hearing about SMRs and learning more about them.
Well, I appreciate the opportunity to meet up with some folks that are technically oriented and still concerned about the environment. And I do apologize for the skipping of the slides. I don't know what was going on.
That was no problem, really, for us.
Thank you. Hope we can keep in touch. And if you let me know, and there are some other interesting presentations, I would like to be on the receiving end and would like to participate.